So let's take one example. Again, from your textbooks, we can choose a question, let's say, on the same page, 276, right? Problem, let's say 6.20, page 276, right? So this case, let me read the equation first. The region between concentric spherical conducting shells are 0.5 meter and 1 meter is charge-free. Again, mention charge-free. So it means that rho v is equal to 0. And given the boundary condition as charge, so determine the potential distributions and the E field in the region between the shells. So again, so we know that. Let's draw together. First one. Okay, let's say this is your spherical shell using the inner radius, let's say A, then the outer spherical shell here with radius of B. Then we mention equation and up to 0.5, the smaller one. So the A actually 0.5 meter, and then the B given as 1 meter. And also mention that at the R equal to 0.5 meter, the V actually minus 50 volt, and then when the R equal to 1 meter, the potential given as 50 volt. Right, so that's your boundary conditions. Okay, so again, since mentioned equation is a charge-free medium, so just use Laplace equation given as del squared V equal to 0. So now this is a different case. So look at your table for the case of spherical. See, in the table. So let me write down the full equation so you can see del squared is equal to 1 over r squared d over dr r squared dv over dr close bracket plus 1 over r squared sine theta and d over d theta. They become sine theta dv over d theta close bracket, and then plus lastly 1 over r squared sine squared theta. Then this one becomes d squared v over d phi squared. All right. So it mentioned clearly in the equations whereby the potential only depending on the radius, isn't it? So again, you can simply ignore this theta term, ignore again this phi term. So because the v only varies by the radius, so just focusing on the r term only as shown here, and we know that this equation will equal to 0 because charge-free medium. So let's equal them. So 1 over r squared d over dr, this one r squared dv over dr equal to 0. So again, we have to move this r squared to the right hand side. So r squared times 0 will have 0. So the r squared here useless. Ignore straight away. And then now we integrate for both sides. First integrations, say left hand side and also the right hand side. So you're going to have this whole term finally. So the r squared, the v over dr equal to a constant, right? 0 got constant. Now the r squared here put down there to simplify. So I have here dv over dr equal to the a over r squared. Now again, come to the second integration. So integrate for both sides, left and right. So you're going to have here, finally it will become a v equal to negative a over r plus b. Agree? So that's how we integrate this term over r squared. So we have negative over r. So that's your general equation of v. So to find the specific equation of v, we need to substitute all the boundary condition given here. Put all inside. So let's say the first case, when the r equal to a, the v becomes minus 50. So put here, put down there. So negative 50. In this case is a over a. A here is your 0.5 meter plus b. So what is your b, guys? We have a b here, a over a minus 50. Is it? So bring this a over a to the left hand side. So the positive. So this is going to be our first equation. Again, put the second boundary conditions as shown here. When r equal to b, your v becomes 50. So put here the v 50 negative a over b plus b. So again now get the b value. The b here is equal to the a over b plus 50. That's your second equation. Okay? So now let's equal them. We know that. Let's equal to 1 equal to 2. So you can see that the a over small a minus 50 is equal to the a over b plus 50. Agree? So let's simplify the equations. So I have here the a here. I have 1 over a minus 1 over b. Now become 100. 50 bring here, positive. So we can simply get the a value become 100 over 1 over a plus minus 1 over b. So that's the value of a, right?
Yes.
So now finding the b using any equations previously shown here, you can find the b from any equations, the first or second, right? So the b is equal to the a over small a minus 50. So put the a value inside here. You're gonna have. So if you want to simplify, also can. So how to simplify this equation? Simplify. So you have your hundreds over b minus a over ab, isn't it? So you can put the ab upside. 100 ab over b minus a. Agree? So the b minus a over ab. So bring outside the ab. So that's your simplifications of a. So here can I have 100 ab over b minus a over a is shown here minus 50. So we can simplify the equation. So we let this a. So you can have the b value become 100b over v minus a minus 50, right? So let's put inside the equations the a value is your a value, and so the v B. So put back the equations. V is equal to negative 1 over R. So the A value become 100 AB over B minus A plus 100 B over B minus A minus 50. So that's your final general equations of potential. So if you want to find the specific value, you just plug in the value of A and B. So you have a shorter equations that represent your specific equations of potential. So the same method, if you want to proceed, we can just use this equation to find the E, negative grad V, right? But this case, referring to the table of spherical, and the case of gradient. So let me write down the value of the equations of grad V, of spherical. So from table, you can see the R component dV over dr plus 1 over R of theta component over R, now dV over d theta plus phi component, this one over R sine theta, and here become a dV over d phi. And again, we know that for this case, the potential only depending on the R component. So we can ignore this term of theta, ignore this terms of phi. So just focusing on this part only. So to find the V or the E, just using the same step with R d over dr, and the whole these equations, which is a negative 1 over R, 100 AB over B minus A, right? And then plus 100B over B minus A minus 50. So we know that if we differentiate, this term will have 0. This term will have 0 because the whole is constant. So just have this one, right? So let's proceed to the differentiation process. So the E here, actually, since all these are constant, so take it out. So negative R component 100 AB over V minus A, and now differentiates 1 over R. So what will I have? Can I have here 1 over R squared. Agree? Negative minus R. So that's why we lost this negative term, right? It's 1 over R squared. So that's going to be your final equations of E, both parameter. Right? So okay guys, so far that's all. So I've given you 3 examples on how to use the Laplace equations. For this case, all the examples having free charge, but you can try yourself to use to solve other examples that having a charge, using Poisson's equations. So if you see from your book, you can see a lot of example. For example 6.9. So this case having the rho v value. So just use the same process, same method, plug in the value so you can simplify. Okay, get the same answer finally. So I think that's all for the lecture of Laplace and Poisson. So I think that's all for today. Okay, thank you. All the best for your revisions later on.